Welcome to Vcare Technical Institute.
You look at that plastic phone sitting on your desk and you just sort of expect magic.
Oh, absolutely. You just punch in 10 digits.
Right. Milliseconds later, a phone rings in Tokyo. Or,
Okay.
even just an office 3 floors above you, it feels entirely seamless.
It does. But if you actually pry open the casing of enterprise telecommunications, that illusion of magic vanishes instantly. It's incredibly complex.
Exactly. So today we are doing a deep dive into that exact infrastructure. We're ripping the lid off. We are acting as your personal senior telecom engineers and technical trainers today.
Which is a fun role to play.
This is. And to do this, we're diving into a serious stack of sources. We've got technical manuals from FS IP PBX. We have Oscom's complete PBX certified training syllabi, yeStar configurations, just really mapping out the invisible high-stakes architecture that actually routes your calls.
Right. We're essentially building a masterclass in telephony architecture today. And whether you are a network engineer, a sysadmin, or even just a business owner trying to wrap your head around your IT infrastructure, mastering this is critical.
Because it's not just plugging wires into a wall anymore.
Not at all. I mean, it is a highly complex matrix of software routing rules, IP telephony, real-time packet switching. It's a completely different world now.
Yeah, and looking through these certified training syllabi, they actually tackle this complexity by breaking it down into distinct logical course modules.
Which is the best way to learn it, honestly.
Right, but to even grasp modern voice-over IP technologies, the manuals ground everything in the physical machine that started it all, right? The PBX, the private branch exchange.
The granddaddy of them all.
Exactly. And reading through the history here, the core engineering logic behind the PBX, it basically just boils down to pure resource pooling.
Yeah, that is the fundamental economic driver behind all enterprise telephony. If we go back to the origins, before software routing, telecommunications relied on actual physical copper wires.
Just massive bundles of them.
Right. So if a business had, say, 500 employees, running 500 individual copper lines from the local telephone company directly into your building would be financial suicide.
I can't even imagine the monthly bill for that.
Oh, the monthly line rental alone would bankrupt the company in a week.
Because, at any given second, maybe only, 50 of those employees are actually on an outside call?
Exactly. The rest are, working at their computers, they're out to lunch, or maybe they're just calling another department down the hall.
Which is exactly why the PBX was invented. It sits securely in your server room, and it acts as this, intelligent gatekeeper. It completely automates what manual switchboard operators used to do.
It does. The PBX basically allows a massive organization to share a very small, very affordable pool of external telephone lines across a massive number of internal staff.
So it's essentially a private mini telephone company operating entirely inside your office building.
That's a perfect analogy, actually. Yes.
It isolates the internal traffic from the external traffic. And, to build that mini telephone company, the architecture splits into two core components, stations and trunks.
Right. The fundamental building blocks.
Yeah. A station is simply your internal endpoint. So the phone on your desk, the fax machine in accounting, or the credit card terminal in the retail shop downstairs.
Exactly. And trunks are the heavy-duty external pathways.
Oh.
They're the connections bridging your private business network back out to the public telephone network.
Okay, that makes sense.
So stations are how your employees talk to each other inside the building, right? And trunks are how they talk to the rest of the world.
Right, which makes perfect logical sense for legacy systems running on copper. But then the manuals immediately pivot to what they call Module 3, VoIP fundamentals.
The big shift.
Yeah, and this is where the architecture completely changes. If everything is digital now, and we aren't running hundreds of physical copper wires through the drywall, the entire concept of the PBX has to fundamentally adapt, right?
It does. It's no longer a massive metal cabinet filled with hardware cards.
Right. It becomes pure software.
Exactly. The introduction to voice over IP, or VoIP, it represents a monumental shift in telephony architecture. In a modern IP PBX environment, the phone system is often just an application.
Like just running on a standard server.
Yeah, just running on a standard Linux server, utilizing platforms like Asterisk or, Orcom's complete PBX. Voice traffic no longer requires its own dedicated standalone physical network of wires.
So the voice data is digitized, it's chopped up into these individual data packets, and fired across the exact same local area network, your LAN, that your computers and printers are using.
That's the packet switching aspect of it, yes.
And the engine driving this packet switching is SIP, right? Session Initiation Protocol. I saw this reference constantly in the networking diagrams, usually operating on port 5060.
Oh yeah, SIP is the fundamental language of modern IP telephony. It is the signaling protocol that these digital devices use to communicate over the network.
So how does that actually look in practice?
Well, when you pick up your desk phone and dial a number, your phone uses SIP to tell the Linux server, hey, I need to initiate a real-time communication session with this specific endpoint.
Okay, but this introduces a massive vulnerability that the manuals highlight heavily. Because if my phone calls are now just data packets traveling on the exact same network we use for standard internet traffic, they are competing for bandwidth.
Yes, they are. And that is a huge problem.
Right, because standard data traffic is bursty. If someone in the marketing department decides to download a massive 4K video file, they completely flood the network with packets.
Exactly. And for data, that's fine. An email packet arriving 2 seconds late doesn't matter. Nobody notices.
But if a voice packet arrives 2 seconds late, you get terrible jitter, robotic audio, or, worst case, the call just drops entirely.
Which is unacceptable for enterprise business. This is the primary challenge of voice transmission over a shared LAN. Voice data is incredibly sensitive to latency.
So what's the engineering solution to this?
The solution is the implementation of a VLAN, a virtual local area network.
Oh, okay, so you basically logically slice the network in half.
Precisely. You use a smart Layer 3 network switch to segregate the traffic at the protocol level. So you assign all the computers, servers, and printers to a standard data VLAN. And then you assign all the IP phones to a dedicated, isolated voice VLAN. But more importantly, you configure the network switch with quality of service rules, QoS.
Okay, and what do those rules do?
They prioritize the tags on the voice VLAN packets.
Oh, I see. So it's basically an invisible carpool lane built specifically for phone calls.
That's a great way to put it. The switch acts like a traffic cop.
So no matter how many massive files the marketing department downloads, the switch will literally hold back those data packets to push the voice packets through first.
Exactly. It guarantees crystal clear audio transmission no matter what else is happening on the network.
Wow, that packet-level prioritization is really what makes enterprise IP telephony actually viable, isn't it?
Without it, the whole system would just collapse under regular office use.
Okay, so once you have that solid network foundation built, you have to configure the software to actually route the calls. And the certified training syllabi stress that you cannot just start clicking buttons at random.
Definitely not. It's a house of cards if you do it wrong.
Right. There's a deeply logical dependency chain, the sort of golden sequence of configuration that network administrators have to follow. It goes extensions, then trunks, then dial plans.
Right, because you can't build a highway system until you know where the cities are and where the border crossings are.
That makes sense. If you try to write a routing rule for a trunk that doesn't even exist yet, the entire PBX logic just errors out.
It collapses, yeah. So step one is building the cities, the extensions.
But the sources clarify a really fascinating misconception here. Because, an extension is not the physical piece of plastic sitting on the desk.
Yeah.
It's a software combination of a device and a user.
Right. Separating the hardware from the human identity is a crucial architectural concept in IP telephony.
Yeah.
The device is just a messy address sitting on the network. It's a dumb terminal.
Okay.
The user, however, is the digital identity of the employee. And by separating them in the software, you enable enterprise features like hot desking.
Oh, I've heard of that. How does that work?
Well, an employee can walk into a completely different satellite office, sit down at a random physical phone, punch in their credentials, and the PBX instantly binds their user identity to that hardware.
That's amazing. Suddenly, that specific piece of plastic just becomes their extension.
Exactly. All their voicemails, their routing rules, everything follows them.
So to build that digital identity in the software, you have to define a few variables. You assign the internal extension number, like, say, 1001. Then you configure the outbound CID, the caller ID, which dictates the public name or number the recipient sees when that user makes an outbound call.
Right. You don't want your personal cell showing up. You want the company number.
Exactly. And you also map an inbound DID direct to inward dialing.
which is incredibly efficient for external communication.
Because instead of forcing a client to call the main company number, listen to a long greeting, and punch in a 4-digit extension.
Right. The DID maps a unique 10-digit public phone number directly to that specific internal user. The PBX intercepts the public number and just routes it straight to the desk, bypassing the main menu entirely.
Such a time saver. And finally, to lock this extension down on the network, the administrator generates a secret. And reading the security protocols, this isn't just a simple 4-digit voicemail PIN that the employee needs to remember.
Not at all. You do not want humans picking these passwords. The secret is a highly complex, cryptographically secure alphanumeric hash. Yeah, it is used exclusively by the physical IP phone to authenticate its SIP registration with the PBX server behind the scenes.
So the human user never even sees it.
Never. It just ensures that a rogue device can't just, plug into a wall jack in the lobby and pretend to be extension 1001.
That makes total sense. Okay, so once the internal users are built and secured, the sequence moves to step 2, trunks. These are the border crossings.
Right.
We configure the SSI trunks provided by our internet telephony service provider to give our isolated island of users a digital pathway out to the public internet.
Or, if we are dealing with a legacy telecom company, we'd configure analog DA/HDI interfaces to accept physical copper lines.
Right, depending on the setup. Which brings us to step 3, the absolute brain of the operation, dial plans and pattern matching.
Yes. This is where the actual routing logic lives.
And the PBX is ultimately just an incredibly fast pattern matching engine, right?
That's exactly what it is. When you pick up your phone and dial a sequence of digits, the PBX compares those digits against a hierarchical list of rules. And to construct these rules, engineers use a very specific syntax.
Yeah, looking at the Extracom documentation, the syntax relies on 4 primary variables. The letter Z represents any single digit from 1 to 9.
So no zeros.
Right. Then the letter X represents any digit from 0 to 9. The letter N represents 2 to 9. And a period, just a dot, is a wildcard that means an unlimited number of digits can follow.
Let's actually apply that syntax to a real-world scenario, just to see the power of the PBX routing engine.
Okay, well, the manual provides a brilliant example of international routing arbitrage.
Oh, the cost-saving one. That's a great example.
Yeah. Let's say a business instructs its employees to dial 00 to make an international call. The PBX administrator builds a pattern matching rule that looks like this: 000 followed by Z, followed by a string of X's, and ending in a period.
And that period is necessary because, as you know, international phone numbers vary wildly in total length.
Right, so the PBX matching engine waits, evaluating the digits as the user dials until it finds the closest match or the user stops dialing.
So the user dials 00, and the PBX instantly recognizes the pattern. But here is the genius part.
Manipulation.
Yes, the administrator has programmed the engine so that the PBX intercepts the digits, silently strips away the 00 the user just dialed, and automatically replaces it with a completely different prefix, a 0 and 1.
Why 012?
Because the network administrator knows that 012 is the routing prefix for a secondary, highly discounted international telecom provider that the company has a contract with.
And the employee at the desk has absolutely no idea this manipulation is taking place.
None. They just dial 000 like they were trained to do in onboarding. But in a fraction of a millisecond, the PBX pattern matching intercepts the sequence, rewrites the digital packet, and forces the call out through the most cost-effective SIP trunk.
It is seamless, invisible financial automation. The company saves thousands of dollars a month, and the user just hears a ringing tone.
It's brilliant engineering.
It really is. Now, that handles the outbound traffic perfectly, but the architecture has to work in reverse, too. What happens when a massive marketing campaign launches, and suddenly a wave of hundreds of customers calls into the business simultaneously?
Right, now the architecture has to shift from outbound routing to enterprise call routing and inbound control. This is where the PBX defines the external customer experience.
And the absolute front door for inbound traffic is the IVR, right? The interactive voice response system. The classic, press 1 for sales, press 2 for support.
Everyone's favorite robot. The IVR is basically an audio menu that listens for DTMF tones, dual-tone multi-frequency.
Those are the specific audio frequencies generated when you physically press a key on your dial pad, right?
Exactly. The PBX translates those frequencies back into digital commands and routes the call down the dial plan. But, if a caller presses 1 for sales and every single sales agent is currently on another call, The system obviously cannot just drop the connection.
That would be terrible for business.
Yeah, so the call transitions into a queue.
And looking at the queuing protocols here, the manuals make a massive distinction between a basic hunt group and an ACD, an automatic call distributor.
They do, and it's a critical distinction.
Because a lot of smaller IT setups seem to use these terms interchangeably, but mechanically they're entirely different beasts, especially when it comes to employee efficiency.
The mechanical difference between a hunt group and an ACD is the difference between a blunt instrument and a precision algorithm.
How so?
Well, a basic hunt group is entirely static. It operates on a fixed list. When a call enters the queue, the PBX always rings extension 1001 first.
Every single time.
Every single time. If 1001 is on a call or ignores it, the PBX moves down the list and rings 1002, then 1003.
Which creates a completely miserable environment for the employee sitting at extension 1001.
Absolutely brutal.
They're taking 50 calls a day, constantly getting hammered by the system, while the employee sitting at the bottom of the list at extension 1003 takes 2 calls and spends the rest of the day drinking coffee.
Exactly. It's an incredibly flawed distribution model. It leads to immediate burnout for your best people.
So how does an ACD fix that?
An enterprise ACD completely solves this through state tracking. An automatic call distributor doesn't just blindly ring down a list. It dynamically monitors the real-time status of every single agent's IP phone on the network.
Okay.
The PBX actually knows if a device is in use, ringing, or idle.
Oh, wow. So it can execute complex distribution algorithms based on that data.
Yes. It can look at the pool of available agents and automatically route the incoming call to the specific agent who's been in the idle state the longest.
That is so much fairer.
It is. Or it can even execute skill-based routing, looking at the caller ID of the incoming client and routing them to an agent who speaks their specific language. It balances the workload fairly across the entire floor.
Okay, so at this point, you've just built an incredibly efficient software-driven PBX. But the training manuals emphasize that building the architecture is really only half the job of a senior telecom engineer.
Yeah, building it is the easy part.
Right, because you also must secure the perimeter, and you have to possess the diagnostic tools to fix the invisible data stream when it inevitably breaks.
It will break.
Exactly. Let's start with the perimeter. Looking at the Eastern Network Interface Guidelines, they strongly recommend configuring the PBX hardware in what they call dual mode.
Very important best practice.
This involves utilizing 2 entirely separate physical network ports on the back of the server. One port is designated for the LAN, and the other is designated for the WAN. I'm assuming this physical segregation is basically a redundancy play.
It provides redundancy, yes, but it also provides critical traffic isolation. The LAN port connects directly to your internal office network switch. That is how the PBX server communicates with the local IP phone sitting on the desks.
Right.
But the WAN port is connected directly to a dedicated, physically separate internet line provided exclusively by your SIP trunk carrier.
Ah, I see. So the real-time voice packets traveling out to the public telephone network never actually touch the office's general internet connection.
Never. And the benefit there is, even if the local ISP goes down and the entire office loses access to their email and web browsing, the PBX server is still pushing SSIP traffic out through that dedicated WAN port.
The phones stay online.
Exactly. The business doesn't stop. But, isolation alone isn't enough. An IP PBX is fundamentally a standard Linux server connected to the global internet, which makes it a highly lucrative target for cybercriminals.
Yeah, PBX toll fraud is a massive criminal enterprise.
It really is.
I mean, if a hacker brute forces their way into your PBX on a Friday night, they can use your SSIP trunks to automatically dial premium rate international numbers over and over again. By Monday morning, you owe a carrier in another country $50,000.
Which is terrifying. And that's exactly why exposing a PBX directly to the public internet without a hardened firewall is just gross negligence.
But locking down the firewall creates a massive architectural headache when you have a remote workforce, right?
It creates a nightmare.
Because if you have a sales rep sitting in a coffee shop 3 states away trying to use a Softphone app on their laptop, they need to connect back to the office PBX.
They do.
But standard coffee shop routers and residential firewalls use NAT network address translation, and SIP packets notoriously break when trying to traverse NAT environments. The audio packets literally lose their routing information.
They get completely scrambled. But the elegant solution to this, which is often built directly into enterprise PBX platforms, is the deployment of a VPN.
A virtual private network.
Exactly, utilizing protocols like OpenVPN or IPsec. When the remote worker boots up their soft phone, the application establishes a heavily encrypted digital tunnel straight through the public internet.
Just punching right through.
Right, bypassing the local NAT entirely and plugging directly into the PBX.
So to the PBX server, it looks exactly as if that remote laptop is sitting physically inside the office on the local LAN.
Yep. The SIP packets flow perfectly, and because the tunnel is encrypted, no one on the public Wi-Fi can intercept the audio stream or steal those SIP authentication secrets we talked about earlier.
It basically solves the routing issue and the security issue simultaneously.
It really is a silver bullet for remote workers.
But even with a perfect VPN and a dedicated WAN port, data streams inevitably experience corruption. And this brings us to the final tier of the training: troubleshooting.
The detective work.
Yeah. In the days of physical switchboards, if a user complained about a dropped call, an engineer could literally just physically walk the line, look at the copper wire, and physically see if a rat had chewed through it.
You could hold the problem in your hands.
Right, but you can't visually inspect a digital packet. If a user complains that their call drops exactly 30 seconds after they pick up, or they are experiencing one-way audio where they can hear the client but the client can't hear them, where do you even begin investigating an invisible data stream?
You have to deploy packet-level diagnostic tools. To troubleshoot modern SIP architecture, engineers utilize an Ethernet capture utility, and the industry standard for this is a program called TCPD-UMP.
TCPD-UMP, so it acts like a wiretap on a digital post office.
That's exactly what it is. You aren't just looking at the outside of the envelope to see if a message was sent. You are intercepting the raw data packets as they hit the PBX network interface card.
Okay, so how do you actually use it?
You run the TCPD-UMP capture on the server.
Yeah.
You instruct the user to recreate the exact scenario that causes the dropped call, and then you extract that capture file.
And then what?
You load it into a protocol analyzer like Wireshark, and you can literally X-ray the digital conversation. You can read the SIP signaling step by step.
Oh, wow.
Yeah, you can see the exact millisecond the connection failed. You can see whether your PBX issued the hang-up command or if the client's router on the other side of the country forcibly terminated the connection.
It removes all the guesswork entirely.
It does. It gives you the exact technical truth.
But the manuals also note that if you are still utilizing legacy analog hardware, say you have a physical DHDI trunk plugged into the wall, and the user is complaining about heavy static, you can't use TCPD-UMP because it isn't packetized data yet, right? It's just raw electrical voltage.
Correct. For analog interfaces, you utilize a port monitor tool.
How does that work?
The PBX literally records the electrical voltage fluctuations on that physical copper line and converts them into a standard audio file.
That is so clever.
It is. The network engineer can just download that file, put on headphones, and listen to the raw electrical signal to determine if the static is being introduced by the local telecom provider before it ever hits the digital conversion layer of the PBX.
It is incredible how deep this architecture goes. I mean, we have traced the entire evolutionary path of enterprise telecommunications today.
We covered a lot of ground.
We really did. We started with the foundational economics of the private branch exchange pooling external lines. We unpacked the monumental shift into Module 3, where physical hardware was replaced by Linux servers, VoIP, and SIP packet switching, heavily protected by prioritized VLANs.
Crucial step, that one.
Absolutely. Then we mastered the precise golden sequence of building extensions, trunks, and those clever pattern-matching dial planes. And finally, we explored the critical necessity of securing those digital pathways with VPNs and utilizing tools like TCP-DUMP to X-ray the invisible matrix of data.
And you know, understanding this architecture leaves us with a profound realization about the future of global communication.
What's that?
Well, when you completely digitize voice transmission and you route it through encrypted VPN tunnels over standard internet protocols, traditional telecommunication carriers start to look like an artificial middleman.
Oh, that's an interesting point.
Right. We are rapidly approaching a threshold where the concept of a traditional 10-digit phone number becomes entirely obsolete. It'll likely be replaced simply by direct encrypted digital identities routing seamlessly across the web.
When a phone number is just an arbitrary string of data sitting in a Linux server, the plastic device on your desk isn't really a phone anymore, is it?
Not at all.
It's just a digital terminal.
Yeah.
And realizing that completely changes how you look at the entire infrastructure connecting you to the person on the other end of the line.